This lecture will cover Chapter 6 and Chapter 7, which includes standard errors, statistical significance, effect size, and confidence intervals. The beginning of Chapter 6, I found it mildly amusing because the author begins by talking about standard error and how it's such a confusing topic and how it really frustrates a lot of students because it's so theoretical. So I guess with that warning, we'll go ahead and jump right into the idea of standard error and why we care about them in statistics. So we'll start with a simple definition. Standard error is the standard deviation of the sampling distribution of a statistic. This definition is a little bit confusing because standard error is actually used in a lot of different statistics, and it changes ever so slightly depending on what kind of test you're running. When we get into actually running statistical tests and we're looking at the statistics formulas, you'll see that frequently the denominator of those is this idea of error, standard error on the bottom. So we can think of this as how much random variation we would expect to see from a sample that's taken out of a population. Up until this point, we've been talking about distributions in terms of individual scores. So if we have groups of people, like a classroom or some kind of sample participants from an experiment, how do we plot those individual scores to create a distribution? We're going to change gears slightly and talk about what's called a distribution of means instead. So here we have a graphic that explains this to help you visualize it. On the far left, we have the overall population of individual scores. And what your textbook asks you to do is to imagine that we're going to select from that population a random sample of scores and compute a sample mean. And here it says n scores. That could be 5 people, 10, 100, 1,000, whatever number you would like in your sample. Compute the sample mean. We would plot that here on the far right on a frequency distribution, throw those people back into the population, and then select another sample of the same size, take the mean, and plot that. And the idea is that we would repeat this process over and over an infinite number of times. Once we plot all those different means, we would call that a sampling distribution of the mean. Let's work through an example to illustrate this. This one is based off of the example in your textbook. It starts on page 50. So for some reason in this scenario, we're interested in the average shoe size of adult American women. So your book points out that it would be expensive and extremely tedious to try to measure the shoe size of every woman living in America. It would be extremely unrealistic. So here we have repeatedly random sampling groups of 20 from the entire population. So you can see here the first sample, we get a shoe size of 7.75. Sample 2 has a mean of 8. Sample 3 has a mean of 7.5, and so on and so forth. In the large blue circle on the left, you'll notice that the average population's women's shoe size is 8. And if you take the 5 subsamples here on the right and average all of those means together, you would find that the mean of those 5 samples also equals 8. So in this case, the sample means averaged together are equal to the population mean. Here we've continued the experiment, and you can see that we have 20 subsamples now, all that contain 20 individuals, and we have the sample means for all of those. So if you're interested, you can now average these all together to see if they equal the population mean. The idea behind using this technique is that if you do this enough times with enough people in your group, you're going to be able to mirror the overall population of interest. For example, if we only drew out 3 individuals and we found that they had shoe sizes of 5, 6, and 7, we're not going to be getting close to that overall population mean. But by creating a distribution of means, we're getting closer to reflecting the overall population that we're interested in. Here we have some output from SPSS looking at our distribution of those 20 sample means. You can see that the average is 8.05, which again is really close to the true population mean of size 8. And you can see down here the expected value of the mean is that 8.05. You also have the standard deviation at 0.368. However, since we're dealing with a distribution of sample means, this is actually our standard error. But conceptually, it's the same thing as standard deviation. We're talking about how the scores vary around that mean. whether it's the actual population mean or it's the expected value of the mean. So we can really think of standard error as the standard deviation of the sampling distribution of some statistic. And like I said before, that will change slightly the formula and equation based on the type of test that we're running. So how much random variation we would expect from samples of equal size drawn from the same population. Your book gives an example. If you pretend that there's only 100 people in your population, let's say that we draw out subsamples of only 3 individuals. If you repeatedly kept sampling 3 people over and over again and averaged those means, it's likely we'd eventually get close to the actual mean of the population. However, what if you were taking out groups of 20 people, groups of 50 people, groups of 80 people out of 100? The larger the sample size that you're taking from that population mean, the more likely it's going to represent the overall population of interest. So the amount of variation that we would expect from samples really might depend on a couple of different functions. For example, we have here, if you take mushrooms, mushrooms come in a wide variety of sizes. There's little teeny tiny ones, there's great big ones. So in this case, we would expect a great deal of variability if we're taking groups of different mushrooms together and averaging them and plotting those means. So we would question whether a mean of 4 in one sample of mushrooms, is that really different from a mean of 6 in another, because there's so much variability. On the other hand, if we take a variable that has a low level of variability, something like blood pH, which tends to be consistent across people, we wouldn't expect a lot of variation. So in this case, we would have means of 7.3 and 7.5 taken from different samples. Are they really that different from one another? So our sampling distribution of means allows us to make these comparisons. This idea of variability is really setting us up for testing hypotheses. So on page 53 in your textbook, they give an example looking at average IQ test scores from a sample of 50 adults in California. So if they find that the sample of those 50 adults has an average IQ of 110, the national average is 100 points, we're trying to determine whether that 10 points is a meaningful difference or whether it's something that can just be attributed to sampling error and variability. So what we're doing with our hypothesis testing is we're going to use probability to determine whether that 10 points is a meaningful difference or whether it's just due to chance and error. Page 53 also gives a brief explanation of something called the central limit theorem. Now, this isn't a math class, so we aren't going to get really into the nitty-gritty details of the theorem and how and why it works. But if you take a step back to think about it, it's really cool because it's really the thing that's driving all of the underlying assumptions of our statistical tests. So the central limit theorem tells us that a distribution of sample means is normally distributed even when the population from which it was drawn is not normal. So if we think back to previously, we talked about skewed distributions. You might have a positive or a negative skew, and it doesn't fit that normal distribution. Instead of using those individual scores, if we use this technique of those distribution of sample means, we can actually normalize the distribution, and this will allow our statistics to run. The second point on here points out that a distribution of means is less variable than a distribution of individual scores. So if you think back to our shoe size example, if you were surveying individual women randomly, you might get someone with a really large shoe size, you might pick someone with a small one, but once we start taking groups of women and averaging those shoe sizes together, odds are that those really extreme values are going to average out and it's just going to be kind of a wash, and we're going to get closer and closer to that population mean of 8. The hyperlink down here on the bottom will take you to a short video. It's only about 3 minutes long. It gives a more thorough explanation of the central limit theorem, and it actually explains it using bunny rabbits and dragons. I think it's a great video. It's really quick to watch, and it definitely will illuminate the concept much more than we can do here, or probably even a better job than what your textbook does. So the link to that will also be posted on our landing page for the course, but definitely take a couple minutes to check out that video. Chapter 6 goes on to talk about the normal distribution and other distributions, such as the t-distribution. I don't want to go into too much detail because we'll cover that more extensively when we get to Chapter 9 and look at t-tests. I did want to point out this graphic though. You can see the purple line is our standard normal z-distribution like we've been working with. You can see the other lines are t-distributions that have different sample sizes. And the way that's indicated is by listing the degrees of freedom. So in this case, we'll come back to degrees of freedom later, but degrees of freedom are a function of sample size, and specifically it's defined as the number of subjects or participants minus 1. So this green distribution on the very bottom is a t-distribution with 2 degrees of freedom, or for a sample of 3 people. The teal kind of bluish one is 8 degrees of freedom, or a sample of 9, and the t-distribution that is orange has 30 degrees of freedom, or 31. So what your book points out is once you start getting more and more participants, the greater number of people you have in your study, the more likely your distribution will mirror the standard or normal distribution. And if you recall, that's the distribution we really like because we could use our z-scores and our percentiles and get a lot of great information about it. So it's an important thing to point out that when we get into running our tests, sample size plays a really critical role in how we're able to find statistical significance. But like I said, we will return to this idea of the t-distribution when we're actually running t-tests. So Chapter 6 does have some formulas and it goes into a lot of detail. And for right now, we can kind of gloss over that a little bit. Don't concern yourself with the calculations. We'll cover more of that when we get to Chapter 9, and specifically we'll be running them in SPSS. I wanted to say just a little bit about this idea of probability and coincidence. Your book talks about it a little bit and just wanted to shed some more light onto it as to why it's important. When we talk about probability, we're talking about the likelihood that a particular outcome will occur out of all possible outcomes. And there's a little interactive activity here that we'll click on. When we're talking about probability, it helps to take a really simple example. This is kind of a fun website. It's a virtual coin flipper. So in case you find yourself needing to flip a coin and don't have any on you, you can always check out this website. So we don't want to get too nitty-gritty into the math details of probability. We're really interested in probability so we can be skeptical that sometimes our results of our statistics could be due to chance or coincidence. So probability for our purposes is the number of successes over the total number of outcomes possible. So when we talk about flipping a coin, what's the probability of getting a heads? There's only one way to get heads out of 2 potential outcomes, ignoring the fact that in a fluke situation, the coin could magically land perfectly on its side, but I'm not sure that happens very often. So we have a 50-50 chance of getting heads versus tails. So let's go ahead and pretend to toss this coin a number of times. We'll start with 10. I just entered 10 and we'll click toss 'em. So our magic coin is flipping virtually, and you can see here our results are listed out. We can also visualize them as a table. You can see we got a perfect 50-50 split, which is kind of cool. And you can also express this as a ratio, or we can move that decimal point to get a percentage. So what happens if we toss even more coins? We'll clear this out. Let's toss it 50 times and see what happens. So here you can see the breakdown. Our percentage ratio has changed a little bit. We have 36% heads versus 64% tails. And you can really play around with this and enter even more. For example, what if we toss it 100 times? We'll just wait a second here for that to come up. And you can see again, we have a 44% heads to 56% tails. If we pretended that we were going to keep flipping this coin, what would happen if it just kept coming up heads over and over again? At what point would we begin to suspect that the coin was rigged or there's something wrong with this website? So that's really what we're trying to accomplish in statistics. We want to know how confident can we be that these results, there's actually something happening and it's not just due to chance or error. That was our brief probability example. So the reason why probability and coincidence is important is because it's really easy to get taken in and see patterns and things that aren't necessarily there. For example, if you've ever been to the casino, you might have someone say something along the lines of, "That woman's been playing that slot machine without success for 2 hours and she just quit. Let's go play that one. It's going to pay off soon." So realistically, it would really be the same odds of winning this machine in those first 2 hours as the next 2 hours. So the idea that the machine is due or it's hot is really just something that we call the gambler's fallacy, is the technical term for it in psychology. Same thing with the second example. My next door neighbor has 3 boys and she's pregnant again. This one's bound to be a girl. Well, from a probability standpoint, the odds of having a boy versus a girl have not changed. Those are independent based on what children you've had before. So it doesn't really matter how many kids you've had and what their gender is. Odds are you have the same chances of having a boy versus a girl. So again, we call that the gambler's fallacy, and that's this idea that the probability of a particular event changes with a long string of the same event. So going back to the coin flip, if I flipped 5 heads in a row and ask you to predict what the next coin flip will be, some people might be tempted to say it's going to be tails because it's due, it hasn't come up yet, but you would still have that 50-50 chance of heads or tails. So your probability of flipping heads for a 7th time is the same as if you were to flip tails instead. So probabilities are never certain. They're always expressed in some kind of a ratio, unless the probability is 1, so a perfect 100% chance of something happening, or 0, which is a perfect 0% chance of happening. And again, we're interested in these long run patterns, not necessarily guaranteeing what will happen. The reason why we care about probability is because this is how we use inferential statistics to test our hypotheses. So specifically, we're using probability to make decisions, in this case, about our distribution of sample means. When we develop hypotheses, there are 2 hypotheses that we want to consider. And just a fair warning that the language in this section gets a little dicey because it's very abnormal. Normal people don't talk this way, but the language that we use around hypothesis testing has to be really specific. So the first one we have here, we have H sub O, and that symbol stands for the null hypothesis. And the null hypothesis means just that, null, nothing, the absence of an effect. So in this case, it's saying that the population mean would be identical to the sample mean. So the notation, we have H sub O, we have the population mean, or the Greek letter mu, equals the sample mean, the X with the bar over it. So the null hypothesis is always saying that there would be no effect. So if we're interested in something like a reading intervention, let's say we have a population mean of reading scores, we think some new program is going to help boost those scores. The null hypothesis would be that the program will make no difference. So the score in your intervention sample would be equal to the general population. It means that our intervention would have had no effect. On the other hand, the second bullet, we have H sub A, which is the alternative hypothesis, sometimes called the research hypothesis. And this is when we're predicting some kind of an effect. So in this case, the population mean will not equal the sample mean. So again, the notation is exactly the same, except we're saying the 2 would not be equal. So with our reading intervention, we might see an increase in the sample, we might see a decrease, but we're just going to make the alternative hypothesis say that the 2 will not be equal. They will differ in some way, shape, or form. When we talk about alternative hypotheses, we can take 2 general forms. So with our reading intervention example that we just said, we might suspect that there's some kind of difference, but we might not know if it's necessarily going to improve scores or if it might actually hurt them in some way. So in this case, we could use what's called a two-tailed test, meaning that we don't have any expected direction for the change. We just know that they're not equal in some way. On the other hand, you sometimes see people using a one-tailed test, which is predicting the direction of a change. So with our reading example, if we're pretty confident and maybe there's previous literature or research to support it, we could say that we think this particular intervention will increase test scores. And we would call that a one-tailed test. Generally, as a convention, you see two-tailed tests used, and that's kind of the standard that we'll be using in this class. But I just want you to be aware of the difference. But for our homework assignments, we'll focus on two-tailed tests. Our other piece of vocabulary that I wanted to cover is this idea of p-values, which are sometimes called alpha levels. So we have a general consensus in the scientific community that we use a p-value called less than 0.05. And that's our threshold for rejecting a null hypothesis. And this number is really kind of arbitrary. You probably have seen it in journal articles. Sometimes people will report an exact p-value, or otherwise they'll say it's less than 0.05, less than 0.01. When you get into medical research, they might use a more stringent level, like a 0.001, and that's because they want to be really confident in their results in that case. But in general, we use a p or an alpha level of 0.05. And in the future, next time we'll be looking at how this is calculated in SPSS and how we can tell whether our results are statistically significant. But for right now, we'll just say that for results to be considered significant, we need a p-value that's very small. We want it less than 0.05 specifically. I mentioned before that the language of hypothesis testing sometimes throws people off a little bit. So I wanted to walk through an example before we move on. So let's say that I have a hypothesis. I have a class of 25 students, and I have a hypothesis that all of the students in the class go to college full-time. So I could ask every single person in the class. However, as we talked about sampling, that just sounds exhausting. I don't want to talk to every single person. So instead, let's say I take a subsample and I only ask 5 people. If every single person said, yes, I go to school full-time out of those 5, would that prove my hypothesis about my overall population of 25 students in my class? It wouldn't, because there could be just one person that says no, and they didn't make it into my sample. So this is kind of the drawback to using samples. When we do research using a sample, we can never prove a claim that we make in a population based on data from a sample. However, this is where it gets kind of tricky. We can disprove the null hypothesis. So like I said before, the null hypothesis always means nothing, no difference, nothing going on. So instead of proving the null hypothesis, what we're trying to do in our research is to disprove the null. So again, we can never 100% prove the research or the alternative hypothesis, but instead we're attempting to disprove or disconfirm the null hypothesis. The real question is, what happens when we make a decision about our null hypothesis, whether we're rejecting it or fail to reject it? What happens if we're wrong? So a lot of times the decisions that we make turn out to be incorrect. So if you reject the null hypothesis, if you reject the idea that there's no effect, and it turns out that we're wrong, the null hypothesis is actually true, there is nothing going on, we call that a type 1 error. In that case, we're saying that there is a difference in something when actually it doesn't exist. So saying that something happened when it didn't. On the other hand, if we fail to reject the null hypothesis, and it turns out that it's really true, we call that a type 2 error. So in that case, we're telling the reader that nothing happened, but in reality, it actually did. Let's walk through an example with this table here. A good example is the courtroom system. In America, a defendant is presumed innocent or not guilty. So our null hypothesis is not guilty, no guilt. If we reject the null hypothesis and convict you as guilty, if you actually are innocent, then we've made a type 1 error. On the other hand, if we find you not guilty, but it turns out you really are, then we would call that a type 2 error. We also call that an OJ error, if anyone's watching the OJ Simpson documentary. So usually in research, we're trying to minimize the type 1 errors, but we're also maintaining that balance or trade-off between the type 1 and type 2 errors. You can see here also on the chart we have, if we reject the null hypothesis, we can actually make a correct decision. So there's no effect, the null hypothesis is true. versus if we fail to reject it. So those are kind of the 4 possible outcomes when we're making decisions about our hypotheses. Another example that sometimes resonates with people is like a pregnancy test. So in this case, if not pregnant is the null hypothesis, if you take a pregnancy test and it says you are pregnant, in reality you are not though, that would be a false positive or a type 1 error. Likewise, if you take the test, it says you're not pregnant, but it turns out you actually are, we would call that a false negative, or it would map onto the type 2 errors. So in statistics, we're trying to quantify the probability that we might be wrong in our decision. And that's when the alpha or p level comes in, because that is our guideline that gives us our probability of committing a type 1 error. So what that means when we're using that guideline is that when we're making conclusions, we're saying that there is a less than 5% chance that the null hypothesis could be true given the results that we obtain in our study. Next, I'd like to change gears and talk about effect size and confidence intervals. Again, your book goes into a great amount of detail about calculating these and different measurements for them. We aren't going to go that far in depth, but I would like you to be aware of what effect sizes and confidence intervals are and what they're used for. And this will come up when we use it in SPSS because it'll calculate it for us. So the main reason we have effect sizes is that the larger our sample is, the more people we have in our study, the easier it is to find statistical significance. So the question then becomes, how do you determine if a statistically significant difference is actually meaningful or what we call practically significant? So for example, if we're looking at average IQ scores of men and women, here we have an average score for men of 100.02, an average score for women of 100.04. If you have only 70 people in your sample, odds are that's not going to be a statistically significant difference. We're looking at 0.02 points between the two, not really statistically significant. However, if you have a gigantic sample size, so things with standardized testing where we're collecting large amounts of data, even the slightest difference in those two means is going to turn out to be statistically significant. But the real question is it considered meaningful or is it of practical significance? Some statisticians will actually call this the sledgehammer effect. So people who work in big data like data analytics at Amazon or big companies or marketing data, they're looking at just huge data sets with tons of consumer information, and they're able to find these statistically significant differences, but odds are they're not really meaningful or have any particular use. So a simple explanation as to why this happens is this really has to do with the fact that the sample size, or n, is in the denominator of our equation when we're calculating standard error. So a large sample will actually yield a small standard error. And then the standard errors are in the statistical test, so it's actually going to influence our significance testing in the long run. There are several measures of effect size, and there's a couple of different guidelines. These are out of your textbook. There are actually different effect sizes you can calculate for different statistical tests. These are just kind of some general guidelines. But the important point is that we always want to look at the context. So if a drug has a small effect size of killing a patient the first time they take it, that's a really meaningful or practically significant thing. But again, going back to our IQ example, we have that really tiny IQ difference between two groups that might not turn out to be so meaningful after all. So to summarize this a little bit, I said before that larger sample sizes are good because they're more accurately reflecting the population, but we always want to be careful that when that sample size gets too large, we need to move beyond just significance testing and look at effect sizes, in that case to tell us if there's a meaningful difference regardless of sample size. Chapter 7 in your book also talks about confidence intervals, and confidence intervals and effect sizes are both becoming increasingly prevalent in journal articles. Hopefully some of this notation will look familiar the next time you're reading a journal article, the results section. And the idea is to really just give the reader more information instead of just saying something is significant, yes or no. We're giving the reader more information so they can draw their own conclusions about the results of the study. So you'll probably be seeing these two things a lot more frequently when you're reading, so it's a good thing to keep an eye out for. So confidence intervals are nice because they give us a range of values that we can be certain, to a certain degree confident that the mean of the population we sampled from will fall between. So let's continue with our IQ example. We could have a confidence interval. We can say we're 95% confident of this interval of 92 to 103 IQ points. And what this is telling us is that we're 95% sure that the mean of the population in our sample represents is going to fall between those boundaries of 92 and 103. So you can see that gives you kind of a buffer zone of error. I sometimes think about it in terms of weather predictions. If you're trying to forecast snowfall, instead of the weatherman saying that we could expect anywhere from 1 to 8 inches, it would be a lot nicer if they'd say, I'm 95% confident that the true number of inches of snow that we get will be between 5 to 7. So we're trying to give a reasonable range and then express the degree of confidence we are, that our actual value will fall within that range. Your book gives a couple of examples, some formulas for calculating confidence intervals around a mean. It's really great to look at from a conceptual level, but again, we aren't going to be calculating these by hand. It'll actually be, I believe, one of the defaults when SPSS runs your statistics. It'll automatically give you a confidence interval. So the really important thing to know is what it is and why it's used for and how to interpret it. So like I said, SPSS has options that we'll be looking at to actually compute the confidence intervals, and you can choose between a 95 or a 99%. Confidence intervals are nice because they're a little more concrete to understand compared to effect sizes because the numbers are in the same unit as your variable. So when we're talking about IQ points, it's in the same measurement as points. If we're talking about inches of snow, it would be expressed in inches versus effect sizes that are more standardized and allows you to compare across studies. So this concludes our kind of baseline chapter, the last of those two, where we're building up our vocabulary and conceptual understanding. Next time we're going to drill down into actually running some tests. I know you're very excited. I know I am. So in the meantime, the book did point out that these chapters are pretty dense and pretty theoretical. So I really encourage you to take some time, let it digest and kind of sink in, and maybe go back and look at it again or read through some notes again. I also plan on posting a couple of different supplementary materials on the website. I found a nice video that talks about standard error. It has a very cool visual, as well as the central limit theorem video that was linked to in these slides. So hopefully between all these resources, it'll really help solidify this understanding, and it'll be useful as we move forward and start testing actual hypotheses.